All right, so this week we'll finish up chapter 3. Should be pretty quick, and then we'll take a look at the beginning of chapter 4. So just a reminder of what a system of equations is, something you did back in Algebra 1, Algebra 2. It's basically when you're solving for 2 or more variables. Okay? So the big thing you have to remember when you're solving a system, you have to put, like if it's x and y, you've got to put x equals, tell me the answer, y equals, tell me the answer. You're going to tell me 2 numbers. Okay? When we're solving a system with 2 variables, which is pretty much what we're going to stick with, we're never going to do more than 2 in this section, you can write your answer, like I said, you can do it like this, x equals, y equals, or because it's an xy value, you can write the answer as a coordinate. So you could write it like this, where that coordinate is going to be a place where the 2 graphs cross. It's pretty much unlimited for how many variables you could solve for. We're only doing 2, but I mean you could do 200. At that point, graphing it on the calculator isn't really going to work because our calculators don't graph in higher than 2D. And even if you had 200 variables, you can't even visualize that. That's really confusing. So you'd use like substitution or elimination, or maybe a matrix. That'd probably be the best way. But 2 variables, graphing works okay. So remember, when you're solving a system, we're basically just looking for where 2 things cross. Now, depending on what we graph, the 2 things could cross a lot of times. Right? It depends on, like, think of 2 lines. Well, there's not really a lot that can happen with 2 lines. But think of like a parabola and a line. Those could cross a bunch of times. You could get 2 times. So the more curvy thing that we're graphing, the more times it can cross something else that might be curved. Okay. And can someone remind me again, how do you find an intersection on the calculator? What do you press? Yep.
Second calc.
Yep, second calc. 5, yeah. Option 5, I think it says intersect. Okay. So we might try something with algebra. We might do 1 problem in this section with algebra, but the focus is really graphing. Okay? Okay. So let's take a look at our first example. So this one says solve graphically. Now, can you take either one of those and put them into the calculator the way they are? No? Okay, well, why not? What do you have to do?
You have to add in the y.
Yeah, we got to get y by itself. So, Brendan, can you tell me my first step to get y by itself in this top equation?
Minus 2x.
Okay, so I'm just going to remember that. Minus 2x, okay. And then my last step?
Divide by 3.
Divide by 3. Okay, so I'm going to do all that in one step. I'm going to minus the 2x. I'm going to write it like that. Still going to have the 5 over here. So he said minus the 2x. And now I'm going to divide everything by 3. That's why I wrote the x the way I did. Okay. Is there any question on how I did that? No, I'm just going to do it like this. So now we've got y equals negative 2/3 x plus 5/3. That's good. Now you can type that in. Eric, can you tell me for my second equation how I would get y by itself?
Plus 3x divided by 5.
Plus 3x, okay. So he said positive 3x. So I added the 3x, the 21 stays right where it is, and then he said divide by 5. Divide by 5, divide by 5. Perfect. Okay, so what I'm going to basically do is put that in y1, put that in y2. And I'm going to be looking for where these two graphs do what? Yeah. Intersect. When you draw two lines, what are the different cases that could happen? There's really three things that can happen when you draw two lines. Anyone describe the different kinds of intersection? Yeah?
It could be perpendicular.
Okay, which is a specific case of the lines doing what?
Intersecting at 90-degree angles.
Okay, so they could cross exactly at a 90. We could just say they could cross in general in one spot. Whether it's perpendicular or whether they cross like this, pretty much the same thing. They're crossing in one spot. What else could happen? You okay? It's okay. So they could cross in one spot, or the two lines could,
Share all their points.
they could be exactly the same line. So you can't even tell. They're right on top of each other. What else could happen?
They could connect.
Right, they could be parallel. So one of those three things is going to happen. Cross once, same line, parallel. Just looking at these real quick, can someone tell me, are they parallel? No, they have different slopes. And I can definitely tell they're not the same line. I mean, they have different slopes, they have different y-intercepts, so they're going to cross once. They'll make like an X shape. Okay, so the way you type it in is like this. Negative 2/3 in parentheses with an X plus in parentheses 5/3. There are other ways to type it in. That's probably the simplest. Okay. 3/5 X plus 21/5. Okay, we're going to do zoom 6 and see. If we can't see the intersection point, we'll just have to adjust our window. Perfect. So we can see it. We're going to do second calc intersect. The guess doesn't matter because there's only one intersection. So no matter where you put it, it'll find it. Maybe it'll take 1/1000th of a second longer if you don't move it closer. But there's your answer. Now, when we write that answer, you have to write both of them. You can either write it just like that, x equals -2, y equals 3, or what's the other way I said you could write it? Yep.
X equals Y equals.
Yep, so that's what that is, x equals y equals.
Yeah.
Or parentheses as a coordinate. Either answer is correct. How you would get this wrong or only get partial credit is if you only told me x. I need x and y. Right. Questions on that? Okay. Let's look at this one. Now, this one just says find the number of solutions. Doesn't actually ask me to find any of them. Just how many. So all we want to do is see how many times they cross. Are they ready to type in? Yeah, they're both y equals, so that's perfect. Just make one of them y1, make the other one y2. Doesn't matter which one is which. No, it doesn't matter. All right, so we've got, let's see, -x³ plus 3x² plus x minus 3. All right, so that's that one. And we've got -2x² plus 5. And again, I'm going to do zoom 6. Start with that. See what happens. All right, so we got a cubic turning twice. And a parabola. So find the number of solutions. How many solutions are there? Yep. 2? Maybe. I don't know. Yep.
If you zoom out more, there might be 3.
Might be 3. So I think we need to look a little bit lower and see if these things are getting closer. So let's set the y min to like I don't know, I just put negative 35. I can definitely see 2. But the question is there something hidden off the screen? And the answer was yes. I don't think I've quite found it, but at this point I can tell they are going to cross. Everyone see it? They're eventually, maybe if I went down to like negative 60, I could probably see it. Now, if I actually had to find it, then I'd need to see it. But to just answer this question, I can tell you that there are 3. 1, 2, and another one right there. Okay, so point to that problem. Make sure you look off the screen for things that are hidden. Okay. Any questions on that? All right, and now the last one in this section, and then we'll do 4.1. So I told you this section was pretty quick. All right, they want us to do this algebraically and graphically. Well, if they ask us to do it algebraically, we know there's something tricky that's some nice thing that's going to happen. All right, when you got a cubic in general, you got to do all the stuff we learned last week. P's and Q's, maybe synthetic division. Something tells me this is going to just work out nice somehow. Now, the top equation is equal to y. The bottom equation is equal to y. Does anyone remember the name of the method you can use here? It's not elimination, but it's another method. Yep.
Substitution.
Substitution. Take what y equals in the bottom and substitute it into the top. And let's see what we get. 3x equals x cubed minus x. Okay, hint here is we should try to do the same thing here that you would do if this was a quadratic. So what should I try to do? Yeah?
Plus x on both sides?
If it was a quadratic, I wouldn't plus x. It's close, but I would do something else. Yeah?
Get all the x by itself.
Well, we'd like to, but you're not going to be able to because you have x cubed and x's. So, what would we do if this was a quadratic? Yeah? So get one side equal to 0. Yes. So, what could we do to get everything on one side in the least amount of steps here? Yeah? Yeah, just subtract 3x. So that's going to give me 0 equals x cubed. And remember, that's 1x minus 3x, that's minus 4x. Now, what can I do on the right-hand side now? Yeah?
You can square it. Oh, wait, no. Here, equal square.
You can't do the square root until you have like a number. Like we got to have like something by itself. Like if you had x squared equals 9, then I'd say yeah, take the square root of both sides, and you'd get x equals 3 or negative 3. But there's a little bit more we got to do. But eventually we might get to that. Yep.
Divided by negative 4.
You don't want to divide here. It's something else we have to do when it's just on one side. Yep.
I have plus 4 to both sides.
No, then it's not going to be equal to 0 anymore.
Oh.
Remember, you want to keep it equal to 0. Yeah?
Why did it change from cubic to square?
That's an excellent question.
Oh, sorry.
Because I made a mistake. It's funny, it's the first one I've ever made. Actually, it's like the 20th one today already. So x cubed minus 4x. Now what can I do on the right-hand side?
Factor.
Factor, yes. What can you factor out?
You can, you can pull the x out.
Now you know why I was thinking x squared.
And then it's x squared minus 4.
Yes. So that factors, and now look at that. That's a difference of 2 squares. That factors again. How does x squared minus 4 factor. Yep.
X plus 2 and x minus 2.
Yeah. Now you've completely factored it. That's as much as you can do. So now set each factor equal to 0, and those are your answers. Okay. So what value could I plug in for x to make the first factor 0? Yep.
-2.
That's the second factor.
Oh, 0.
Yeah. So we got the first, the second, and how about the third factor? Yep. 2. Now, I made this little table because you're only half done. I mean, in terms of the work, we're like 95% done. But there's still 3 more answers we have to write. We've got 0, -2, 2. I still need to find the what?
Y.
Still got to find the y's. So use the formula right here. I think the easier one to use is the bottom one. Take your x value, triple it, and there's your y. Okay. So what's my first y value?
0.
Second one? Third one. Perfect. So you could write your answer in a table like that, or you could write your answer as coordinates. 0, 0, -2, -6, 2, 6. Okay. So that's how we would solve it algebraically. Now graphically, I'll just show you what it would look like. So let's type in x cubed minus x and 3x. So we already know we're going to have a line, we're going to have something that curves, and it's got to cross it 3 times because we got 3 answers. So 1, 2, 3. Okay. I'll find one of them. Second calc intersect, and I'll do the one that's up over here. And it says, I don't know if you can see it or not, 2, x is 2, y is 6. That's the last one. So what's kind of a pain about this one, you'd have to do that 2 more times. Right? If you had 7 intersection points, you're going to have to do second calc intersects 7 times. So it just takes a while. Okay. Any question on how we solve that one with algebra? Or how to do it on the graph? And you'd have to do it two more times. Okay, so I don't know why, but last week on the test, a lot of people had trouble with this. I don't know if it's because they're trying to go like this. They're trying to trace and just get like as close as they can. And they say, oh, it looks like it's about 0.15, -0.14. No, don't trace. Just do second calc, and it'll calculate the exact value without you trying to guess. Okay. All right. So that's it for 3.7. So last thing we'll look at, and we'll spend most of the time on, is 4.1. Okay, so what we're looking at in 4.1, I'm just going to skip ahead and just kind of show you what the problems look like. They look like that. Or that. These are what we call rational functions. So a rational function, first of all, rational means it's a fraction. And you would have a polynomial in the top of your fraction and a polynomial in the bottom. Here's another example. F of x equals x squared plus 1 in the top, x minus 3 in the bottom. Now, there isn't really much of a restriction on what polynomial you can put in the top. You can put anything in the top. You just, in the bottom, can't put 0. Okay, because if you put 0 in the bottom, you'd be dividing by 0. Can't do that. Okay, so there's an example of a rational function. And here's an example of another one, g of x. 3x squared minus 4x plus 1 divided by x squared plus x minus 2. Okay, we're going to learn to look for some patterns here. like certain things happen if the exponents are equal. Something can happen if the exponent in the top is bigger. Different thing can happen if the exponent in the bottom is bigger. And by exponent, I mean the biggest exponent. Right, so we're going to look at that through all of chapter, up through 4.2. 4.2 we're going to do tomorrow and Wednesday. That focuses mostly on sketching. So we'll do lots of sketching. The last section of the week, 4.3, that focuses more on solving an equation. That's all algebra. So any questions on rational functions? Or just what they look like? All right. So nothing like negative exponents. Because remember, negative exponents would be, you don't want to have negative exponents because that would give you something like this. We don't want to have fractions within fractions here. Okay? We just want a nice simple polynomial on the top, a nice simple polynomial on the bottom. Not this. That's kind of complicated. Okay, now you got fractions within fractions. The other thing you don't want to have is square roots like that. You can't have a square root and have it be a polynomial. Okay? So all the exponents have to be positive integers. Okay? Technically this means this. 1/2 is not an integer exponent. That's why you can't have square roots. Okay? So nice positive whole number exponents. Okay, so because we have fractions, one thing we got to look out for now is do not make the denominator 0. So, one thing I will ask you about these kinds of functions, what's the domain? So the domain is everything except what would make the bottom 0. So what I usually do is I figure out, okay, what would make the bottom 0, and then say, all right, the domain is everything except that. So in example 1a, what is the domain? Chris?
Everything except 3.
Everything except 3. So remember the way we want to write it is with that U, the union symbol, and 2 intervals. Yeah, go ahead.
Infinity. 3.
3, remember, not including 3.
Not including 3.
Yep.
Or, no, and.
Or.
Or.
Yep. That means or.
Including 3, infinity.
Not including 3 to infinity. Perfect. That means all real numbers except 3. Okay. Any questions on how we found the domain? All right. Let's try one that's a step harder. B. 3x squared minus 4x plus 1 divided by x squared plus x minus 2. And I'll give you a hint. There's something you're going to want to do to the bottom. And we did this just like 2 minutes ago in one of the examples. Anyone know what I'm going to want to do to the bottom? Yep. We're going to want to factor it. Because factoring makes it easy to find the zeros. If this doesn't factor, it's a quadratic, you're going to have to use quadratic formula and find the answers that way. Okay, but hopefully it factors. Okay, first term in each has to be x and x. What about my signs?
Plus and minus.
Yep, I'm going to need a plus and a minus. And 2 numbers that multiply to give me 2. Yeah, right, good.
2 and 1.
2 and 1. And I'm going to do them exactly in the order he said. Let's check it. X squared minus x plus 2x. Yep, plus x, and 2 times negative 1 is negative 2. Perfect. So, what's my domain on this one? can just say it, let's say it in words and then we'll write it using the U symbol. We'll do that after. Chris?
Everything except -2 and +1.
Yes, all reals except -2 and 1. Or, if you want to write it as an interval, you're going to need 3 of them. Basically, you're going to write this. I'm just kind of showing you guys a visual so you can see it. There's a hole at -2 because you can't use it. There's a hole at 1 because you can't use it. What can you use? Everything from here down, everything from here to here, and everything from here up. 1, 2, 3 red sections. So now describe each one of them. Okay, so -infinity to -2, or can someone give me my middle section? Yep, Jerry.
-2 to 1.
-2, not including it, to 1, or someone else give me my my last section. Yeah.
You're including 1 to infinity.
Not including 1 to infinity. Perfect. So that's your domain there. Okay, let's look at one more. Now, I think C is actually a step easier than B because look, they've already factored the denominator for you. Okay, let's not do this one in interval notation. We'll just write it in words. Okay. What's my domain here? Emily?
Every number except 2 and -4.
And what kind of numbers are we talking about? When you say every number? Sure. All reals except, can you just say them again?
All real numbers except 2 and -4.
Yep. So the domain is all reals except 2 and -4. Okay, so just a little practice finding the domain, and that's also going to come in handy for finding something else in a little bit. Any questions on that one? Okay. So the simplest rational function you can have, okay? Like A, that's kind of a complicated one, right? B is even more complicated. C, that's also pretty complicated. This is the simplest one you can have. 1 over x. Okay, that's called the reciprocal function. So let's graph it and see what it looks like. Okay, so 1 divided by x. So technically that is a polynomial over a polynomial. That's a constant in the top, which technically is a polynomial, and then just a linear variable in the bottom. I'm going to do zoom 6. Now that's kind of what it should look like. I'm just going to kind of tweak that a little bit, just fix it. I just want to move it. There we go. All right, so it kind of looks like it stops. Like if you follow it going up the y-axis, looks like it just stops. It should stop. Okay, this part. Try blue, but we'll see what happens. This part should just keep going up. This part just keeps going down, to the right, to the left. That's what the graph of 1 over x looks like. The reason it has trouble sketching it is because when things start to go basically straight up or down, the calculator starts to freak out because it can't graph things that fail the vertical line test. So it just stops. That's the graph. So we're going to look at a couple things on that graph. First, I want to look at this. Remember, this means as x approaches infinity. That means as you head to the right. Okay? The one on the left, or the other one here means as x approaches negative infinity. Negative infinity is on your left. So look at this graph and just kind of, actually it might be easier from the calculator. If I go to the calculator and I just trace along, what happens to y as x gets bigger and bigger? Get my y value.
It's smaller and smaller.
Smaller and smaller, getting closer to what?
0.
0. Will it ever reach 0?
No.
No, because even if you take 1 and divide by 1 billion, is 1 divided by 1 billion 0? No. It's extremely small, but it's not 0. Okay? So as you head further and further and further to the right, your y value approaches 0. Now, let's look at it the other way. What happens as you head further and further to the left? Wait for it to jump over to the next section. What's happening to my y value as I head further and further left? Yeah.
Getting bigger.
And what's it approaching?
0.
It's also approaching 0. It's just one of them is approaching 0 from the negatives coming up. The other one is approaching 0 from the positives down. But either way, as x approaches infinity or negative infinity, your y value, remember that's what f of x means, your y value is approaching 0. Any question on that? All right. So the fact that as you approach infinity or negative infinity, you're getting closer and closer to something, that's called an asymptote. Specifically, this is called a horizontal asymptote. So basically, if I were to take and put in the line y equals 0, and what I'm going to do is I'm going to draw it as a thin, very, very thin line. If I can, I want to do it as a thin dotted line. Yep, I can. Okay, so I'm going to put a very, very thin dotted line at y equals 0. I'm going to hit graph. I don't even think you can really see it unless I blow it up. You can kind of see there's like a red dotted line. It's right on top of the axis. Look at that red dotted line and that blue curve. You know what? Actually, it would be even easier if I go like this. Let's take my axes and if I make them off, you'll be able to see the line better, I think. Here's the original. Here's that dotted red line. Can everyone see how the blue curve and the red dotted line are getting closer and closer and closer? Kind of looks like they're right on top of each other, but they're not. They're just getting extremely close. Anytime that happens, that is called an asymptote. So, to find an asymptote of a function, look at what's happening in your function as x gets really big. Really big positive number or really big negative number. Either way. Okay. So these are both examples of functions with asymptotes. Some people think when you have an asymptote, it means you can never cross that dotted line. That's not always true. The function on the left, right here, that's an example of something that's getting closer and closer to an asymptote, and it's never crossing it. The function on the right, it actually does cross it earlier on. But then as you continue heading further and further right, it doesn't. Okay? We haven't done trig yet. You could also have something like this. Here's my asymptote. So that's a function that it's getting closer and closer and closer and closer to the asymptote all the time, but it's constantly oscillating above and below, above and below, above and below, above each time, but getting closer and closer as you go. That's another example of an asymptote. You guys won't have one that crosses over and over like that. You might have one like this. perfectly fine to cross an asymptote near the origin, but as you continue heading left or right, it's just going to get closer and closer eventually. Okay? It's not going to keep crossing forever in this section. I think page 217, they've got some more pictures in your book if you want to see some more types of pictures like that. So let's look at this one and let's find the horizontal asymptote. So first thing you always want to write down is the letter and then equals. When we have a horizontal line, what is the letter you put on the left side?
X or Y.
Y. Right? Could be y equals 0, could be y equals 5, it could be y equals something, but it's got to be y equals. And the reason I'm telling you to do that is because next we're going to look at vertical asymptotes. Verticals are x equals. Okay. On the test, some people mixed all of those up. They just switched the letters. Horizontal has to be y equals. Vertical has to be x equals. It's just the way it works. So now, here's your equation. Y equals 1 over x plus 2. Now, in that equation, let x get really, really big and tell me what y is approaching. So first thing I do is I look at this fraction. If x gets bigger and bigger and bigger, what's happening to that fraction? Getting smaller, and what is it approaching? Just the fraction part. Jared?
Just the fraction.
Just the fraction part.
0.
This fraction part is approaching 0. It never will be 0. But if you take 1 divided by like a trillion, it's like 0.0000000000001. Very small. So you're taking a number that's extremely close to 0 and adding 2 to it. So basically, you're going to get an answer that's extremely close to what? Yeah?
2.
2. That's your horizontal asymptote. Y equals 2. Now, let's say x was, let's just pick a big negative number we can do in our heads. Not that big. 1 divided by negative 1,000. That's negative 0.001. If you add 2 to that, I plugged in negative 1,000 for x. What's negative 0.001 plus 2? Yeah?
1.999.
Yeah. So if you plug in a big negative number, you're going to get a number that's extremely close to 2, but a little smaller. If you plug in a really big positive number, like 1,000, you're going to get 0.001 plus 2, 2.001. So really close to 2, but just a little bigger. Right? But you're getting an answer that's pretty close to 2. And that's your horizontal asymptote. Okay. Anyone think they can tell just by looking, without really plugging anything in, what the horizontal asymptote will be here? Yeah, Emily? Negative 3. Basically, if you've got a fraction with a variable in the bottom, that fraction is going to turn into 0. Or it's extremely small. So horizontal asymptote, what is it? What equals negative 3? Y, yes. Okay. Any question on that one? I'm not worried about graphing that. Okay, now I'm going to bring our graph back up, but I want to look at a different spot. And let me turn my axes back on. And let's make them black. Okay. Now, I don't want to look at what's happening as you head very far to the left and the right. I want to look at what's happening as you head to the origin, okay? As you head towards 0. what's happening, let's say, as you travel along this section. So if you're riding on that path in blue and you start heading to the left, what happens? Yeah, okay.
Do you get away from the 0?
So can you say it again?
The line tries to get farther away from the...
Okay, so it's moving away from 0. What happens to it? What does it start moving towards?
Y. The origin.
So yeah, as you travel, so what's happening to the y value of this curve in blue as you get closer and closer to the origin? Yep.
To increase it.
To what?
Infinity.
Infinity. Right? If I go into my table on my calculator, I can't plug in 0 because that's a divide by 0. But if I try something very close to 0, like 0.1, my y value is 10. Let's try something even closer. 0.001. Now my y value is 1,000. Right? 0.000001. Now my y value is 1, 2, 3, 4, 5, 6, 1 million. So the closer and closer and closer that I get to 0, the higher and higher and higher my y value gets as I approach from the right. What's happening as I approach 0 from the left side? Like that. My y is heading down forever. So the two things we're going to describe here is as you approach 0 from the right and from the left. And I'm going to show you how to write it. So as you approach 0 from the positive side, this is the positive side, this is the negative side. As you approach from the positive side, this is the notation that you write. This means as x approaches 0 from the right. Plus sign means from the right, positives. Your y value approaches infinity, okay, because it curves up. So what do you think my notation would be to approach 0 from the left side? 0 with a little plus means from the right, because plus numbers are on the right. Yep.
As x approaches 0 with a little minus.
Yep. As x approaches 0 from the left side, from the negative numbers. That was this way. My y value drops down to negative infinity. Okay, what we're basically looking at here is another type of asymptote. Right? If all of a sudden you try to get close to a value, and all of a sudden it just takes off in curves, that is called a vertical asymptote. And it's very important when you write the equation for a vertical asymptote, x equals. You cannot put y equals. If you put y equals, you just told me a horizontal, which is good. I might ask for a horizontal. But if I ask for a vertical, I want x equals. And it's x equals, and then you put the number that you were trying to approach, and all of a sudden it just went crazy and took off. So, visually, this is what it means to have a vertical asymptote. So x equals 0, or x equals 2, or x equals h, whatever number h is. That number, h, is a vertical asymptote if, as you approach that number, all of a sudden, your graph either goes to infinity, or your graph goes to negative infinity. Now, sometimes it does the same thing on both sides. It can actually do something like this. As I approach 0 from the left, it goes up. As I approach 0 from the right, it goes up. It's okay. It's just, they're both going up. But as you approach, it might not always be 0, but whatever number you're approaching, it's got to all of a sudden just take off towards infinity or negative infinity. Now, algebraically, it's very easy to find vertical asymptotes. You guys basically already did it in the first problem in this section. Remember when I said finding the domain is useful for something else? Well, if I go back to the three problems you guys did, you said the domain here was all real numbers except 3. 3 is the vertical asymptote. Domain here was all real numbers except -2 and 1. Guess what the vertical asymptotes are? -2 and 1. So the domain is basically giving you the vertical asymptotes. The vertical asymptotes are all the numbers that are not in the domain. Okay. So let's write that down. Okay. So if the numerator and denominator don't have any common factors, then the vertical asymptotes will be when the denominator is 0. Now that common factor thing, that's kind of important. Let's say you had x minus 2, x minus 3 over x plus 1. In that function I just wrote, can somebody tell me what value would make the denominator 0? Yep. -1. Let's graph it. Let's see what it looks like. X minus 2, x minus 3. So x minus 2, x minus 3 divided by x plus 1. Now, Brianna said that -1 was the vertical asymptote. So that means as we get near -1, all of a sudden this graph should just take off. Maybe it goes up, maybe it goes down. I don't know. Let's see what happens. All right. So I might need to zoom out a little bit, but can people kind of tell that all of a sudden it's going up when you get near -1? If I go higher, you might be able to see it better. There's other things happening in this graph I'm not going to tell you about today. Maybe you notice it, but look, as you get near -1, look what's happening. All of a sudden, just takes off. Now, let's see what happens if I make a small change to the top. Let's take that graph and go like this. Now you've got a common factor. You have an x plus 1 in the top, you have an x plus 1 in the bottom. I said that you will have asymptotes if you have no common factors. Now you've got a common factor. You still can't plug in -1, right? If you plug in -1, that's a divide by 0. But look at your graph now. Is that graph going crazy near -1, like going up still? No. What do we have at -1 now that we've talked about before? But you can't see. Yep.
The gap.
Yeah, we have a small hole. Okay? If you have a common factor, common factors lead to holes. Common factors will give you a hole in the graph. So as long as you don't have a common factor, then it's okay. Then you'll have a vertical asymptote. Okay, let's find the vertical asymptotes here. Okay, example 4a. Are there any common factors in the top and in the bottom there? Sam?
Actually, 1b.
Yeah, technically if you wanted to put a 1 like this, you could do that. But can that factor ever equal 0? Chris? No, because it's a constant. So we're not worried about that common factor. 1 is a common factor to everything. But let's just focus on that part. So we don't have any common factors that are significant, like x minus 2 in the top would be a problem here. So we are going to have a vertical asymptote. Where's it going to be? Yep, Gary. 2. And how would you write the equation of it?
X equals 2?
Yes, x equals 2. There's your vertical asymptote. How about this one? Example 4b. Where's my vertical asymptote here, Emily?
X equals negative.
Yep, x equals negative 3. Now, what if I did this? Make this plus 1, or minus 1, make it a minus 6. Where's my vertical asymptote now?
Still x equals negative 3.
Yeah, just kind of in your head, process, filter out the information that doesn't matter. This minus 6 isn't important. This minus 6 would control the horizontal asymptote. Okay? This plus 3 here controls the vertical. So don't worry about that number on the outside when you're finding a vertical. It does not change what makes the denominator 0. Questions on that? All right. I'm not going to graph that. All right, let's look at this one. It says find the horizontal and vertical asymptotes, and then we'll describe some transformations. Okay, and I'll help you with the transformations because we haven't done that in a little while. Now, what's a little weird about this is it's not in the right format. When you want to describe like asymptotes and stuff like that, you want a number over a polynomial and then plus or minus another number. That's what you want it to look like. That's exactly what this one looked like. A number over a polynomial. If I go back another page, just look at this one. A number over a polynomial plus or minus a number at the end. So you've got to make it look like that. Not like that. So the way we fix this one is you have to do out the division. Actually divide this into that. And then we're basically going to write our answer as quotient over original denominator plus remainder. Okay? And just to kind of show you with numbers, if you had 14 divided by 5, what's the quotient when you divide 14 by 5? Bless you. Oh, Jared? Jacob? Wait, did I call you Jared? I'm sorry. I meant to say bless you when you sneeze and then with the further. Jacob, what's the quotient when you divide 14 by 5?
2.8.
Just the quotient.
14.
That's my numerator. Quotient is the whole number part when you do 2. And my remainder?
0.8. Or 4.
4. Yeah. So, quotient, remainder. You can basically, I'm going to show you what to do here, and then we're going to do the same thing up above. Quotient plus remainder over denominator. 2 plus 4/5, or 2 4/5, which is 2.8. So let's try it here. X minus 5 divided into 2x minus 13. Let's get the quotient first. What's 2x divided by x? Well, Caleb, what's 2x divided by x?
Me?
Yeah.
Okay, X.
Yep. No. No, that would be 2x divided by 2 would be x.
That should be 2.
Yes, it would be 2. Now multiply back out. 2 times x. 2 times negative 5. And does anyone remember what I do with these columns now? Subtract. That's gone. Negative 13 plus 10. Negative 3. So I'm done. I've got my quotient and I've got my remainder. Do this. Okay? So we've got quotient plus, well actually, what is my remainder? It's going to be minus, just because it's a negative. So quotient minus remainder over my original denominator. Now you might say, well yeah, you said to get this though. That's the same thing. If you want to write it that way, write it like this. Negative 3 over x minus 5 plus 2. Now you should be able to see your vertical asymptote, which you could have seen before. But what you couldn't see before was the horizontal asymptote. So now, I'm not going to do the second part. I just want to know the horizontals and the verticals. All right, let's make sure we get the right letters. Horizontal, what letter? My arm hurts. Yeah. What letter? So we need letter first, and then I'll come back to you for that. But yeah. Yep.
Y.
Y equals, and for vertical, x equals. Just don't make that mistake and mess those up. Okay, that's the easy part. And now K has said y equals 2. Because remember, horizontal, let x get really, really big. Okay, if x is 1,000,000, you're going to have negative 3 divided by 1,000,000 minus 5 is just a little smaller than 1,000,000. It's like 999,995. It's still dividing by a huge number. Okay? So this is going to approach 0. 0 plus 2 is 2. Okay? So there's your horizontal, and that you could not see looking at the original problem. Okay, so we had to do the division. The vertical you could have. What's my vertical asymptote in this problem? Yeah.
5.
5. Yeah, and I could kind of see that the way it was originally. X equals 5. Okay, so any question on that? Okay, so let's look at, I think this is the last problem. So, the last problem, it's going to be a mixture type problem. Okay? Now, just to kind of get you thinking along the lines of what you have to do, you have to be able to figure out the answer to that, to do this problem, or problems like this. If I said to you, in front of you, you have 50 ounces of liquid. Out of those 50 ounces, 35% is acid. So your solution strength is a 35% acid solution. How would you figure out how many ounces are actually acid if only 35% out of the 50 are acid? It's kind of like if I said to you, you got 35% right out of 50 questions. How many did you get right? Same idea.
I would set up a proportion.
Okay, so yep, you could set up a proportion.
I remember, I feel like we did this before.
We did something kind of like this before, but this is going to be easier. Before we had to do like a system of equations. We're not going to have to do that. So you could do a proportion. But there's even an easier way which your proportion would lead you to, but you can jump to this step right away.
You can just multiply 50 by 0.35.
Yeah, and if you set up a proportion, that's exactly what would happen. Just multiply 50 times 0.35, and that means out of the 50 ounces in front of you, 17.5 of it ounces is acid. Maybe the rest of it is mixed with water, something like that. Okay, any question on that? That's all you need to be able to understand to do the last example. Okay, and I'm actually going to use these numbers in the example, so it'll save us a step. So, you've got a 50-ounce solution in front of you that has 35% acid in it, 35% concentration. You're going to pour in X ounces of 100% pure acid. So what you're trying to do is you're trying to make your solution a little stronger. Right? Maybe you need a 50% acid solution. What I want to do is find a graph of the concentration as you continue to pour in more and more acid. Well, just logically, what's going to happen to the concentration if you keep pouring in 100% pure acid? You just keep pouring it in, just keep pouring it in. What's happening to it?
It's going to approach 100%.
Now you said approach 100. Will it reach it?
No.
No. Because you started with something that wasn't perfectly pure acid. So I don't care if you dump in 10 million ounces of acid. There's still a little bit in there that wasn't. So the concentration will approach an asymptote of 100%. Or if you think about it like Eric said, we might be using decimals, like 0.35 or 100% is 1. Okay. So concentration is basically amount of acid divided by total liquid. So let's figure out the amount of acid we have. There's two sources of acid in this problem. We started with some sitting in front of us, and we're going to add some. Okay. How much acid was already in the solution before we even started? Just sitting right in the container.
17.5.
Right. 35% of this number was already acid to start with. We already figured that out. 17.5. How much pure acid am I going to pour into my liquid? Yep.
X.
I'm pouring in X ounces. After I do that, that's how much acid I will have. What I started with plus what I added. Now we want the total liquid. What's the total liquid that I started with? Yep.
50 ounces.
Started with 50 ounces. And how much liquid am I adding? X. That is a formula for the concentration. And they want us to graph it. Okay, so let's graph it, see what it looks like. So in parentheses, make sure you, parentheses will help here, plus X divided by 50 plus X. Now, let's think about our values. X is the amount of acid you're adding. What's the smallest amount of acid that I could add?
0.
0. I could just say, you know what, I'm going to leave it the way it is. The maximum, there is no maximum. Let's just go up to 250 ounces. Now, why is your concentration as a decimal? When you have a percentage as a decimal, it's always between what two numbers?
100?
As a decimal.
0.
0 and 1. So we can't go any higher than 1. Now, can your concentration in this problem actually go down as low as 0?
No.
No, we're not diluting it, right? It's starting at 35%. If we don't do anything to it, it's going to stay there, or it's going to get even stronger. So I would say we don't even need to go lower than 0.35. So here's a graph of the concentration as you continue to add more and more acid. What do you notice after a while? Like something kind of happens at first, but then what happens after a while?
It starts leveling off.
Right, it's kind of like your grade in a class. Right? When you take a first test right away, your average changes a lot. Then you take the second test, it can still change a lot. If you had a class with like 50 tests in it, by the time you take the 51st test, it's not really going to make that much of a difference because you already have so many other test grades. Same thing here. As you add more and more and more, the concentration starts to level off. It never really flattens out. But if you want to get it up to like a 99% concentration, well, you'd be better off to just take your 100% pure acid and just dilute it a little bit. Why would you use this one and try to bring it all the way up to 99%? You know, it's a lot of work. So, the last thing they want us to figure out is they want us to take the concentration up 40%. They want us to bring it from a 35 to a 75% strength. How much acid would we have to pour in to make that happen? This is going to kind of tie in with what we did in section 3.7 now. Anyone have a guess what I would have to add to this graph to figure out the answer? Yep.
Another line.
Yep. And where's the line going to go?
75 or 0.75.
0.75, exactly. That line represents where it hits a concentration of 0.75. So second calc intersect. If you add about, actually it comes out exactly 80 ounces. If you add 80 ounces to the original solution, it'll bring it up to a 75% concentration. Alright. So 80 ounces. That's it. Okay, so on the test, you will probably have a mixture problem. I would probably split it into two parts, just like this. Give me an equation for the concentration, part one. And then part two, how much acid would I need to do something? Like bring it up to 70% or 20, bring it up 85%, whatever. Any questions on that? Okay. So homework tonight on page 207, 8 through 10. That's just solving intersections, first part we did. And then page 222, it's 3 through 7 odd, 11 through 23 odd, 31, 37, 38. And then question 48, there's parts A, B, and C. Okay, I don't want you to do part C. You just have to do part A and B. All right, and we'll take a look at that tomorrow.